Much. Thanks very much for the invitation. It's really a pleasure for me to be here. It's my first time here in Brazil, actually my first time here in South America. Okay, so I was asked to give an introduction to the Imperial model program, so I apologize for many of you that know this stuff very well, but I'll try to look at my own, at my point of view of this stuff. So just to begin, I'd like to fix the setup. For the first time, for this talk, I would always assume that any variety we're working with, it's a projective variety, non-mind projective. If you know what it means, it's nothing very important, but it's cofactorial. Anyway, what is important is that it's always going to be projective. And for these two talks, I will always work, although many things can be extended in a different field, but I will always talk about projective varieties defined over the complex numbers. And also, as a matter of notation, I will always fix the dimension, and I will denote it by n. So the goal of the Imperial model program somehow is to understand projective varieties. So I would like to start with a very, very easy case where we can already see many things happening. So very briefly, I will say something about surfaces. So the way I would like to look at it is to construct a directed graph of surfaces. So directed graph means a graph where the edges have an orientation from one vertex to the other. So what is this directed graph? For me, for this, in this context, the vertices, you can imagine it would be algebraic surface, smooth algebraic surfaces. Oh, projective surface, sorry. And what about edges? So edges of this graph are, of course, we need to give two projective varieties, two algebraic surfaces, x and y. So an edge corresponds to a map F, which, for instance, we can think of it to be a composition of blow-ups. OK, so if we do that, we obtain a big, big graph with many, many vertices, of course. And the reason is because if we start from any variety x, I can always find infinitely many, as many as the points of x are, varieties above x. Just take any blow-up of any point, you can find many and many of these arrows. Now the question is, OK, what can we say about this graph? What do we know about this graph? So one interesting thing is that we care about connected components of this graph. We care about which one are connected components. So a connected component of this graph corresponds to the rational class of an algebraic surface rational components correspond to rational classes of all these algebraic surfaces. Namely, it could be taken as a definition, or it could say that two algebraic surfaces are birational if they're isomorphic outside the proper subvariety. And it happened to be that if this happens, then they are exactly the same connected component. So I can go from one to the other by connecting with edges. OK, so now the question is, what can we understand about this graph? So one thing, again, we cannot try, given a variety x, given a point x, there is no way to understand what is going to go up. It's too difficult. There's too many stuff. But we can try to understand what is below x. So we define an endpoint. Actually, sorry, maybe I should have said that. There are no cycles. There is nothing like, so the way we define this graph, it's easy to say that there is no cycle, oriented cycle, which means there is no way that we have something like this. So this doesn't exist. Of course, this is completely trivial. In higher dimension, this becomes a bit less trivial. And we'll see it in a few minutes. So what are the endpoints? Endpoints are those vertices that do not emit any edges started from it. Vertices which do not admit any edge starting from it. OK, so what does it mean? It means that, again, there's always a way to go up, but there's no way to go down. Now, what we would like to understand is what are the endpoints in this graph? And actually, and this would be crucial, we can also ask for what I'm going to say next. We can also ask another question. We can ask how many are the endpoints of a connected component. So maybe I should have said, sorry, of a connected component, of a given connected component. So let me start from the second question. I mean, again, for surfaces, everyone knows the answer. But let me start from the second question just to give an example. I mean, it looks like, it's trivial, of course, it's nothing difficult. But we can immediately see there is a difference between two classes of varieties, those that are uniruled and those that are not uniruled, namely those that are covered by rational curves and those that are not covered by rational curves. So if X is uniruled, then there exist always infinitely many endpoints. So again, uniruled means that, sorry, what did I write? Uniruled. Uniruled means it's for each point there exists a P1, a non-trivial map from P1 to the variety which passes to the point. So why is that? Well, I mean, let me give an even more specific example. If you look at P2, then in the same connected components, there is also there is a book surface. So, of course, there are infinitely many of these objects, and they're all birational to each other. So they're all in the same component, connected component. And it's very easy. They don't omit, well, except for one. Well, sorry, let me say n different from one. They don't omit any edge starting from it. So they are really endpoints. So let me say a few words, I mean, one word before I go forward. So I should say that this is Fano, of course. In other words, the canonical bundle, it's anti-ample. It's negative, it's ample. This one, of course, is not Fano, but it emits a map to P1 for which general fiber is Fano. It's P1, of course. So this object here, and actually we can even say more. We can say that the Picard number, the relative Picard number is equal to 1. So this object here that emit a fibration, of course, this is a meta-fibration to a point, for which the fiber is Fano, they're called Mori fiber spaces. OK, so what about the other side of the picture? What about if X is not uniruled? Then there is always, should I say, of course, there is always an endpoint, but it's this endpoint that happens to be unique. There is always a unique endpoint. In each connected component, of course. So, and actually, we can say much, much more. We can characterize the endpoints. So, in other words, X is going to be an endpoint. In this, if it's not uniruled, if and only if the canonical device is an F. So we know very well what it means to be an endpoint. We know very well what we're looking for. And this pretty much the characterization is given by this fact. So I should say, probably Vlad will talk about it. We know even more. We know that Kx will be semi-ample. So in other words, there is a map exactly like here into something for which Kx is the pullback of an ample. But I'm not going to talk about this today. OK, so now the question is how to generalize this picture. I mean, what happens in higher dimension. So one thing that happens here, I didn't say smooth projective variety, is, again, I apologize because many of you know this stuff very well. So we need, somehow, if you want to work with projective variety which have dimension greater or equal than 3, then this one, something like this still holds, but it becomes much more complicated. And the reason is because there are many more blow-ups. We can blow up curves and so on. So the picture becomes quite a bit complicated. And it turns out that working only with algebraic surfaces, with algebraic varieties which are smooth, is not the right category to work with. So we need to work with singularities. And I will try to explain. Actually, my talks, both this morning and this afternoon, it's about singularities. But before I explain about singularities, what are the singularities involved and why we care about them, I would like to say a bit more about what we need to work with. I mean, almost all the results that I know in the minimum of the program are proven with some kind of induction. So it turns out that working with projective variety is not a good place to do induction. And I will explain with a very, very simple example. So let's suppose that we have a rational normal curve of degree n in Pn. So, and let's take the cone over C. So inside, what are Pn plus 1? Of course, I'm assuming that this Pn lives in an upper plane of Pn plus 1 and so on. So the picture is something like this. So this is C, and the vertex I'm going to denote it by P. And let's take a line on this. Let's take one of the ruling of this cone. So what happens? What happens is that, again, we would like to do induction. We would like to reduce the dimension. But if you look at what is Kx plus L restricted to L, it would be very tempting to say, OK, adjunction tells us that this is equal to KL, which is P1, of course. But it turns out to be wrong. I mean, it turns out that the singularity of P are in such a, bad enough to make this formula to be wrong. So we need a correction term. And the correction term, if I remember correctly, is 1 minus 1 over n. Here the coefficients are important. Again, we go back to coefficients, very important. But at the moment, it's just a number, which is less than 1, times p, where p, of course, is the vertex that we're considering. So what happens is that it's not enough anymore to work with varieties. We need to replace x by, in the setup we had before, by some pair. In this case, the delta would be equal to the error, 1 minus 1 over np. So what is delta? So delta, it's a linear combination of hypersurfaces. Where so Xi are just an hypersurface. Irreducible hypersurface, I suppose. And AI, exactly like there, it's a rational number within 0 and 1. Sometimes, well, we want 1 to be included. OK, so now, if you want to try to generalize the picture we had a few minutes ago to the case of pairs, we do need to understand the directed graph in a bit more careful way somehow. So again, I'm not working anymore in dimension 2, but I'm working dimension higher than 2. I'm not working anymore with smooth varieties, but I'm working with singular varieties. And I'm not working with varieties, but I'm working with pairs. So now I want to construct the directed graph. OK, so what I'm going to do is the opposite to what I did before. Instead of defining, it doesn't make much sense, but it doesn't matter, it's all very vague. Instead of defining first the vertices, I define first the edges. Of course, again, It's not very, I mean, of course, I need to tell you something. But first, I want to tell you consider all the possible pairs, OK? And then I'm going to tell you which one are good and which one we throw away. OK, so what is an edge? So in order to do that, I need some definition. So, OK, sorry. We want to define edges. So before doing that, I need some definition. So first of all, let's suppose that x to y is a rational map. It's a rational map. So we say that phi is a contraction. So it's a kind of a weird definition. But I mean, if you think a little bit, it's actually very natural. So if the inverse of phi, which goes from y to x, does not contract any divisor, or any upper surface. So what does it mean? Of course, phi minus 1, I mean, the inverse of phi is not defined everywhere, but surely it's defined over a point of codimension 1. So it's a correct definition. I mean, it makes sense to talk about what happens to phi minus 1 for upper surfaces. It doesn't make sense to say about curves, but it makes sense about upper surfaces. But why do I bother about this? Well, it's very simple. I don't want cycle as my picture. If you remember, I didn't like cycles. So the first thing is not the only thing, but the first thing that I need to assume is that if you take a blow up, from y to x, this is, of course, sorry, I'm changing my notation all the time. So this is, of course, a contraction, because the inverse does contract. The inverse does not contract any upper surface. So then phi is a contraction. But of course, I could look at it at the inverse point of view. Phi, so let me write but. If I look at phi to the minus 1, which goes from y to x, it's a perfectly well-defined birational map. But this is not a contraction. Why? Because the inverse, which is phi, will contract the exception divisor. So we don't like this to work with. Although it's a birational map, we don't like to work with it. It's not a contraction. It's a little bit of a twist, but basically the idea is that you want y to be simpler than x. So you don't want that the opposite will destroy things. I mean, the opposite of phi will destroy things. OK, so again, it's just a definition. And it's very natural, just that at the beginning it might look a bit weird. OK, this is the first definition. The second definition is slightly bit more technical. So let's suppose that now we have two pairs. So let's suppose that, let's suppose that x delta is a pair. It's a log pair, exactly like before. So log pair just means what is written here. So sorry, I should have written it here. It just means some variety which is normal, which emits some divisor delta. I'm assuming x is 2 factorial if you're worried about being Cartier. And this is true. So let's suppose that x delta is a log pair. And let's suppose, exactly like before, that phi from x to y is a contraction. OK, we say that phi is kx plus delta negative. So the definition, again, I'll try to justify why it's a good definition in a sense, but it might be a bit obscure again. So if there exists a resolution, a log resolution, also of the indeterminacy of phi, so in other words, we have something like this, which makes, these are two proper maps, which if you want W, it's smooth. Actually, sorry, it's not. a resolution of the indeterminacy, not quite of the singularities. Okay, so you have a variety W, which is normal, but the most important thing is that you miss two morphisms, P and Q, from W to X and Y, which makes this diagram commutative. So what happens is that what we want to be true is that if you look at the difference between Kx plus delta and Ky plus the straight transform of delta on Y. So of course, if phi was an isomorphism, these two would be equal. But they're not equal. I mean, there's a difference in general. And the difference would be only in the exceptional locus, in the locus where this map is not an isomorphism. So I need to add a term which is E. And what I require about E is that it's effective by even more. So I should say why I need even more. Well, let me write first what I need, and then I will explain. And such that the exceptional locus of Q is equal to the support of E. So the support is just the union of all the divisors which appear in E with positive coefficient. And of course, the exceptional locus is where Q is not an isomorphism. OK, let me say why we need this. Why we need this assumption? Well, you should think of it to be, if you're familiar with these pictures, a composition of divisorial contraction and flips. What I don't want is flops. I don't want anything that behaves like flops. And the reason is because I don't want cycles. So although it's a very technical assumption, let me say that it's very easy to show that by doing this, you cannot create any cycle like before. But before I do that, before I talk about cycles, let me say a few more words about this picture. Actually, so now we know what is an edge. An edge is going to be just a birational contraction, which is Kx plus delta negative. So the edges are going to be birational contraction which are K plus delta negative, correspond to the set of all the edges of our graph. OK? So now I need to tell you what are the vertices. Again, at the moment, I took all of them. I took all the possible pairs. But now I want to throw away many of them. And it's about singularities. I mean, which singularity do I allow to be true? So I should define what is, in this picture, what is a Covain-Matalot singularity, or log canonical. So X delta is said to be Covain-Matalot terminal we will be back in this, mostly in the second talk, if there exists Y gamma above X delta. So I'm going to explain what it means to be above X delta. Yeah, such that, in other words, there exists phi, which is an edge, from Y to X, which is a birational contraction which is Ky plus gamma negative. And of course, delta is equal to the push forward of gamma. So to be above just means that there is an edge above X delta which satisfies the property of being an edge, of course. So of course, at the moment, I didn't say anything. I could take the isomorphism. I mean, it's not a very interesting definition. So I need to assume something about Y gamma, which is exactly what you expect. So, and Y gamma is log smooth. With coefficient, since at the beginning I say that the coefficient could be within 0 and 1 included, so I need to assume that, and the coefficient of gamma are strictly less than 1. Okay? Log canonical means less or equal than 1. So if you want the definition of log canonical, So there's no condition here. Log smooth, of course, is going to be log smooth and so on. So it's, again, it's very unclear, it's very untechnical. But what is the idea? The idea is that, exactly like in the case of surfaces, we want to have in a connected component a nice representative. We don't want to work with wild stuff which doesn't have anything which can be of any use. So again, the connected components looks very, very wild, very large, very big. But there will always be one term, at least one term, of course, infinitely many if there's one, which is log smooth. Okay, so this is the set of edges, the vertices we want to work with. Oh, what does, yep, sure. So log smooth means that y smooth, all the components of gamma are smooth, and they're simple normal crossing. Sorry, I made more. Okay, so in other words, you take, the picture would be something like this. A surface, for instance, where you consider sub-varieties which meet transversally, and these are the components of gamma. Of course, a pair which is log smooth, which is Kawamata-terminal, sorry, could be singular. It could be something like this. If you choose the right coefficients, this is Kawamata-terminal, but it's not log smooth. But this is both Kawamata-terminal and log smooth. Okay, any other questions? Okay, so let's see. So I would like to explain why this picture is useful. Why we really need somehow, the way we understand something, it's related with this picture. But before we do that, let me very briefly, since we talk so much about this graph, let me talk about the end, what we are looking for, the endpoints. So the questions are exactly the same. What are the endpoints? And again, I'm not going to write about in each connected component. And also, for this particular talk, I will care about how many are the endpoints. Of course. Oh, I see. Yes, it's correct, yes. Yeah, that's right, yes. The exception device, yes. Yeah, definitely, yes. Because you can extract all those that have low discrepancy. Yeah. So it's not the standard definition, but it's still OK. Thanks. OK, so these are the two questions that I'm going to try to explain. That I'm going to aim to today. We care about both of them, of course. We care about what are the endpoints, because the endpoints are the good representative of our diagram. But my personal point of view, it's also interesting to understand how many of the endpoints there are. So you can expect that there are two pictures, two cases, two big families. Those that emit infinitely many endpoints, which resemble us about P2, and those that emit only few of them. But the problem is that many of these things are still conjectural. They're not quite a theorem. So let me say what is the conjecture. Oh, sorry. Before I state a conjecture, let me say a very easy fact, which somehow justify this definition. Actually, two facts which justify this definition. The direct graph does not emit a cycle. This is not trivial, but it's not difficult. So what does it mean? Of course, there are cycles in the sense that it's not simply connect. What I mean by cycle is directed cycle, of course. So there's nothing like this. Of course, there could be something like this. By cycle, I mean directed graph. You cannot go back to the same point. And that's exactly why I need this weird definition. Because if you remove this part, there would be flops and there would be plenty of cycles. OK, that's the first fact. The second fact, which also just somehow justifies this definition, maybe I should give you one more. So is the fact that if kx plus delta is an f, then x delta is an endpoint. This is easy to prove. Namely, you cannot find something like this if kx plus delta is already in f. Okay, so these are somehow the candidate for being endpoints. Maybe I should say one more thing, which I'm not going to talk about because I think Vlad will talk about it. If phi is a bidirectional contraction, so it's an edge, then the canonical ring, so I'm not going to define because I'm sure Vlad will define it, but the canonical ring, which is the set of all the sections, of all the global sections, sorry, of all the twisted power of this, it's invariant. So what does it mean? It means, well, up to torsion. So what does it mean? It means that if you care about the ring of sections, doing this kind of operation, again, here you need to have this property. Otherwise, it would be easy to find counterexamples. Does not change this ring. So we have a big, big connected component, but they all have somehow the same ring. OK, so these are, again, not difficult facts. Nevertheless, there are many, many things which we don't know about this graph, so which very briefly I would like to state. And then I would like to mention why I care about termination of flips. OK, so let me state the conjecture very briefly. So let's suppose that x delta is a Cavamatter optimal pair. Then we distinguish two cases. Exactly like in the case of surfaces. So if kx plus delta is not Z-effective, OK, so maybe I should remind you what Z-effective means. So what it means is that there exists an IMPA A. Basically what it means is that it's in the closure of the effective divisor. But a formal definition would be there exists A ample such that mkx plus delta plus A is not big for some big value of m. It's a weird definition. I mean, you probably saw a better definition than this, but this is correct, I think. OK, so if this is true, then we expect that there exists an endpoint. Actually, we know that there exists an endpoint, sorry. Then there exists an endpoint below x delta. What does it mean below? Well, it's a graph, right? So it makes somehow sense to talk about below and above. Such that, so let me call it y gamma, sorry. Such that y gamma emits a modifiable space. What does it mean? In other words, there exists phi is a bad letter, eta from y to z, such that the fiber are log Fano, such that if f is a fiber, ky plus gamma restricted to f, the negative of this is ample. And this map is non-trivial, maybe I should say. So what does it mean? If you remember, in the case of surfaces, we had two kinds of fibration, either the trivial fibration to a point or the P1 fibration. So somehow this is a very natural generalization of that picture. And again, I'm going to go back to this in a few minutes. So somehow, I think this is a nice point of view to characterize endpoints. Okay, and what is the opposite case? So far I talk about one family, those that are not Z-effective. So the second case is the opposite. If not, so it's not worse. If it's Z-effective, then there exists an endpoint which is minimal. So again, y gamma, and minimal means exactly like in the fact, ky plus gamma. Sorry, endpoint below x delta, of course. This is very important because we don't want to make it more complicated than x delta. So blah, 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 blah is an f. Okay? So again, we have two almost opposite sides of the medal. The case of kx plus delta is not Z-effective when we expect something to be similar to a Fano variety, and that where it's similar to a minimal surface. In other words, there is no -1 curve. Of course, situation is more complicated than that, but the idea is very simple. I mean, the idea is that nothing else can happen. Okay, again, very briefly, what are the known results? Tim Blood will talk about this. So I care more about the known results. But first of all, thanks to Mori and many others, in dimension 3, everything's OK. Then, with Birker, Ekman, and McKern, a long time ago, we proved that 1 is OK. And then, so if kx plus delta, actually, we know a bit more, but if kx plus delta is big, or delta is big, then it's also OK. So we do know something. Why? I mean, these two are similar, but I'm not going to spend any time on it. But why is this somehow interesting? Is because if you take delta equal to 0 and kx is big, this is an important case. It's varieties of general type. So for varieties of general type, everything works well. OK, so again, I want to know more. What is not OK? Well, what is not OK is existence of minimal models in general. So what else do we want to know? And again, I didn't say anything much about how many there are. So I would like to talk about these two cases, which are very much related within each other. So what happens if, so what about in general? OK, so actually, the opposite of this is true. If it's an endpoint and we are, so we forget about 1, OK, because 1 is OK. At least for the time being, I will forget about 1. I will only care about 2. So 2, OK, it happens to be an 2 also here. Being an endpoint is exactly equivalent to being F. I mean, it can be shown that, I mean, we know existence of flips, so really we can be sure that they're pretty much equivalent. I mean, being an F or being an endpoint. OK, so what is the problem? What could happen that is wrong? I mean, how can we possibly have a counterexample? So what don't we know? So we don't know if there exists, in general, we don't know if there exists an infinite path. And this is, as weird as it can be, it's in every case, well, except in dimension 3, of course. In any case dimension higher than 3, even when we assume that everything is known from the point of view of the conjecture, we don't know if there are infinite paths. So 1 is not, I mean, in this case, it's not known. I'm going to go back in this in a few minutes. And also, when it's big, we don't know if there are infinite paths. What does it mean? It means that we know a graph. We know there exists a graph. And we could be very much having a path which is arbitrarily long. Again, the graph is very, very big. But in particular, it could be something like a tree. But in particular, do we know if there exists a path that is arbitrarily long? We know that there are paths which have infinitely many endpoints. Even P2 has a graph which has infinitely many points. So for sure, so this one we don't know. For sure, something like this can happen, right? Even P2 blown up in 9 points, this can happen with infinitely many. So there are two cases. This is OK. I mean, this can happen. We need to live with that. But this one, we're still far away from understanding whether it's true or not. So somehow, this problem is very much related. Actually, it's equivalent to another problem, which is called termination of flips. So the conjecture, it's funny because I'm not going to talk about flips at all, although I'm going to talk all the time about termination of flips, just that I hide flips somewhere. So I don't know if Vlad will talk about flips. There exists no infinite path. Sorry. The conjecture, which is called termination of flips, says that the statement is that there exists no infinite path inside the direct graph. So you cannot find something like that. You can find many, many of these, but you cannot find something like that. OK, so why is the conjecture important? I would like to give two motivations why I really care about this conjecture. So the first one is that if we know how to prove this conjecture, then maybe I should say this conjecture was the minimum of the program. So I'm going to call MMP. And this one is called termination. So if we know termination, then it's easy to prove that this implies MMP in the way we stated it. In other words, if you know that this conjecture is true, there are no infinite paths, then you always end up in a minimum model. Again, we only care about two because one is known. But I would like to talk about something else, which is also interesting. So it's about finiteness of modifiable spaces. So of course, this is false. The way I write it is false. Why? Because, well, again, I say P2 has infinitely many modifiable spaces. But nevertheless, something's true. And I would like, something might be true. And I would like to explain what is that. So now I'm going to talk about this. And again, it's very much related with this conjecture. OK, so let's suppose that we have a pair X delta. And exactly like before, I'm going to denote it by AI SI, where I care about this time. Goes from, maybe let me change it. I think I didn't use indices, so I'm not cheating. I'm going to start from 0. OK? And let me assume, of course, it's a strong requirement, but it's not so natural, that if I denote A at 0 times 0, this is ample. Of course, at 0 is totally useless, but it's just a matter of notation. Of course, it's not an ample device, but it's a non-ample Q device, because at 0, it's not an integer. So in other words, some multiple of A is very ample. OK, so in other words, just a matter of definition, I'm going to define B to be equal to the sum from 1 to K of AISI. So in other words, all I'm done, it's purely arithmetic. Delta is equal to A plus B, where this is ample and this is nice. I mean, it's still LT. OK. So I'm going to write one more conjecture. Which I think is nice. Oh, I should say that maybe Vlad will talk about it. In the case of 2, in the case of K plus delta not uniruled, we expect only to have finitely many models. But it's related with big conjecture like the Kuhn conjecture and so on. I care about the other side of the story. So let me go back to finiteness of modifiable spaces. So under those assumptions, which is very, very weak, there exist only finitely many modifiable spaces or endpoints, which are just endpoints below X delta. Sorry. Okay, what are the assumptions? There is almost no assumption, really. The only assumption, which is very strong, but I'm hiding it, is that this is ample. Besides that, there is no other assumption. Okay. So why do I need an assumption? Well, because if you don't have that assumption, it's surely false. So let me write it one more time. If you take P2 blown up in 9 points, so this is the first example that everyone consider when you want to look for something weird, amidst infinitely many modifiable spaces. Sorry. And points below. Okay, so what is the picture? The picture is that no. It's not the base. It's X. It's Y. What are denoted by Y? It's not the base. No. I just mean the variety where the edge, where the modifiable space starts, modifiable space starts. So, for instance, there is a Brooks surface. It's an endpoint. The domain, not the codomain. So, I don't care about. Yeah, that's right. Sorry. Yes. No, I'm not saying. Although even that. No. I'm not talking about that. I'm only talking about. Yeah, think about P2 and it's a Brooks surfaces. Although, of course, this one only has one probation. I'm only talking about that. Yeah. Sorry. Thanks for remarking. I'm not talking about the base of the modifiable space. I'm only talking about the domain. So those that are rational, like you say, those that are rational to X. So the good example is, so this is a good example. So there are infinitely many blowdowns of -1 curves. And somehow these are endpoints for something. So I don't care about what is the probation below. Okay? Or if you want, forget about modifiable space. Just think of it in points. Okay. Any question? Okay, so let's see. What was I talking about? Okay, so what is wrong here? I mean, why do I state a conjecture which seems to have a contradiction? Well, of course, I already mentioned a few times. This is crucial. You're not going to find delta equal to something ample for which this works. There's nothing like that, because otherwise this conjecture would be false. And clearly, this conjecture is true in dimension less or equal than 3, because termination of flips holds. Oh, sorry, I didn't say that. Yeah. So let me prove. I would like to give a proof, which is very simple, in the next 10 minutes, of the fact that so I don't know. Maybe I should say fact, but I'm going to prove it. But I wouldn't call it theorem, because it doesn't deserve to be called theorem, I think. So let me call this, finiteness conjecture. So termination is equivalent to finiteness. Termination is equivalent to finiteness. Or at least termination for the connected component that might emit a modifiable space, it's equivalent to finiteness. So let me prove it. I mean, I'm going to prove this fact. It's very simple, but it's somehow instructive. Okay. So I'm always working with that assumption above, first of all. So let's suppose that delta is of the form A plus B, and this as above. So what it means is that A sample and B is like there. So one thing that is very easy to prove, but is nice and is false here, is that then there are only finitely many vertices starting from I should say that this is, again, not a theorem, nothing. But, I mean, I talk a lot with this about this with Birker, and McKernan. And probably many more people, but again, it's just observation. So then exist only finitely many edges starting from x delta. So let me prove this. I'm going to skip some details, of course, but the details are classic. So I want to show that what happened for P2 bar P9 points cannot happen here. In other words, you cannot find something like this, infinitely many edges starting from x delta. So how do we prove that this is the case? So suppose not. So we know, although I didn't say it, we know that each edge somehow corresponds to kx plus delta extreme array. So I'm sorry, I will use some technical language. But again, it's very classic in the Miyamoto program. So there is Ci for each vertex, for each edge. There is C, sorry, which is kx plus delta negative extreme array. So very briefly, what does it mean? So the cone of curves, it's a form, the compactification form a closed cone inside a finite dimensional vector space if you take up two numerical equivalents. So extreme array means just the ray which are vertices to this cone somehow, the one-dimensional rays. Kx plus delta just means that kx plus delta times c is negative. All this means. What is interesting is that more or less there is a one-to-one correspondence between each edge and these rays. Okay. So this is the only technical thing that we need to prove the fact. Okay, so in particular, kx plus delta times c is negative. This is because it's kx plus delta negative. Okay, but what is this? No, it's purely arithmetic. This is kx plus b times c plus a times c. Okay, this is also very simple. And so this implies that a times c is less than minus kx plus b times c. Again, very simple. So, but what else do we know? There's a theorem of Kawamata, which is not trivial, of course, which says that we can bound this number. So I'm not going to talk about it, but it's a theorem. This is always less than 2n, where n is the dimension of x. And so probably you see where I'm going, because this follows from the fact that it's extremal. Because I have a fixed ample guy, and all these curves have bounded degree with respect to this ample. So of course, there are only finitely many. So this is the end of the proof. Okay, any question? Actually, we can prove more using this trick. Which is kind of weird, actually. I was surprised. Even ending to x delta. Well, excluding which are not divisible conduction, of course. So this one, I'm not going to prove it, but it's not difficult. Also, I'm not going to use it, so it's not difficult. But somehow it's interesting to know that around x delta, there are not too many wild things that happen. Of course, I'm cheating. I'm removing all the blow-ups. But if you remove blow-ups, there is nothing else. There are finitely many objects. Yes? Oh, no, I'm assuming that there is an ample component, always. Sorry. What I said is that, I say but I didn't write it. So termination inside the directed component, the connected component of x delta. Sorry, where delta is equal to a plus b. I think I mentioned it, but I didn't write it. I didn't prove, sorry, I didn't prove this one yet. I just proved, sorry. Yeah, I'm making a confusion. So I just proved this fact so far. I'm going to go ahead. Okay, thanks. Okay, yeah, sorry. So now I prove this. Using this fact, I will prove this. So the proof is very simple. Okay, so what happens is that there is no such a thing as infinitely many. So each vertex has bounded degree. Each vertex has finite degree. This is in graph theory. Has finite degree. Actually, there's a theorem, I think, called by Koenig, something like that. In graph theory, that says that we're done. If you have a graph where this is satisfied, then you almost say like something like this. It's finite if and only if there is no infinite path. But although it's, there's a proof you can find in Wikipedia, but although, it's something very, general, I'm gonna just prove this fact by drawing a graph. So let's suppose termination is not true. So in other words, suppose that there is an infinite path. And so on. So what we know is that each of these guys, has an endpoint. So each of these has an endpoint, which is so for instance, this one is an endpoint, has an endpoint. So here it's an endpoint. Of course, it could be that the endpoint, So we know by as a fact that each guy has an endpoint. So this one has an endpoint, wherever it is, it doesn't matter. Suppose now we take this guy here. This also has an endpoint. Okay? So it's possible that it's the same endpoint, but still, this guy is also going to be as an endpoint, and so on. So you see that if this path exists, since I cannot say that the endpoint for this is here, because I cannot go above. Maybe I can say the opposite, but I cannot say that the endpoint of this guy is here, right? I cannot go this way. There are no cycles. I can only go down. So if you look at this picture, somehow you convince yourself that the infinite path will correspond to an infinite number of endpoints. So there exist infinitely many. Well, there might not be difference. But suppose, okay, this one is after 10 steps. Then you choose the 11th step, and you will have, it must be at some point, right? Let's say at the 20th step, they are the same. But then you go to the next one, it will be not the same anymore. Does it make sense? It's a kind of you can write a formal proof, but it's really elementary. Suppose that the endpoint here is the same as this one. It needs to be at some point, right? So suppose it's the same here. The first one corresponds to the 20th one. Then you choose the 21, you create one more, and so on. You will be always able to create infinitely many. Does it make sense? OK, I'm running out of time. So pretty much the same picture with this fact here implies the opposite is true. Namely, if you only have, what do I need to prove? So what I prove is that if there are finitely many endpoints, then termination is true. So the other way is exactly, looking at these graphs, maybe you do a better job than me, give a proper proof. But the idea is that there are no graphs with infinitely many points below something, assuming that this property is true, unless there is a path. Unless there is a because for each of these guys, there is one endpoint. Yeah, sorry. What I prove is that if there are only finitely many endpoints, then this path cannot exist. And the opposite is pretty much the same. Again, if you don't believe me, it's a lemma that is written somewhere. It's called Koenig lemma, which has nothing to do with minimum of the program. It's about graph theory. All it says is that if there are no infinite paths, then assuming that this is true, which we proved, then there are only finitely many points. OK, I'm running out of time, so I will stop here. Later on, I will talk a little bit about termination and how we hope to prove termination. OK, thanks very much for your attention.